All right, so let's start with the last passage calculation. So I'm sure every one of you knows what this model is. So we look at the quadrant of the integer lattice. So do you see my pointer?
Yes, we do.
Oh, very good. So for each side in the lattice, we assign a random variable Gij, and these random variables are related between each other by the following recurrence identity. Okay, so the Gij variable is defined via its neighbors from the bottom and from the left, and this identity involves random variables Wij, where Wij in our case will be independent random variables with geometric distribution. So for each side, we have an independent random variable with the geometric distribution depending on the parameter q. All right. And if we apply this identity like recurrently, we can write the formula for the random variable g while the weights w. So we have this formula. Oops. We consider all the paths which go upright paths which go from the origin to the point Mn. So for each path, I call it pi, we assign the energy, which is the sum of the w's along this path, and then we maximize over all these paths. And we apply the random variable g. So this is the simplest case of the last passage calculation model. Of course, you can so you can consider the path pi not going just from the origin, but from some curve. And then, so this model will be slightly more complicated. So there is some variety of the initial state of this model. Okay, so we're interested in the so-called KPZ scaling limit of this random variable g. So more precisely, we look at the point Nn, and we aim to send n to infinity, and we consider the following asymptotic expansions. So we have a linear term in n with some constant c1, and then the fluctuations of order n to the 1/3, and psi n is some random variable. So we have random fluctuations of this order, and we can also vary this the endpoint Nn. So we can look at the points along this diagonal line, which is in red in this picture. And so for each point in this line, n minus x, n plus x, we write the same asymptotic expansion in n. We have a linear term, and we have fluctuations of order n to the 1/3. But now the random function h will depend on x, and we expect to have fluctuations of order n to the 2/3. Along this line. So Hn will depend on x times n to the minus 2/3. Okay, so if we choose all these three constants suitably, so you can see the formulas for these constants, they depend only on q. Then it was proved by Johansson that psi n and Hn have limits. In particular, the law of psi n converges to the Tracy-Widom GUE distribution. And the function Hn converges as a function to a process, Airy process minus parabola. So A is the Airy 2 process. So, and again, if we allow this path to go not just from the origin, but from some curve, then the limits will change. In particular, the limit of H will be, like for suitable initial data, it will be the KPZ fixed point, which is a generalization of the Airy 2 process minus a parabola. Okay, so about this, we'll talk a bit later. Yeah, so Johansson wanted to know what is this point x at which the path gets the maximal energy. So this point x, then the one which maximizes energy, it is a random point. And in principle, in the discrete setting, there can be several of them. So he has chosen one of them, for example, either the most right one or the most left one. And he wanted to study the asymptotic behavior of this random point, this maximizer of the energy. Okay, so capital Xn will be the location of one of these maximizers, the most left one or right one. It doesn't really matter. So what we know is that the function Hn converges to the Airy plus minus parabola. So we would expect that this maximizer X will converge to the maximizer of the Airy plus minus parabola. And so this is the conjecture which Johansson made. So basically he said that the Airy plus minus parabola should have almost surely a unique maximizer. To be more precisely, he said that on any interval from minus L to L, the maximizer of the Airy plus minus parabola is unique, almost surely. Then, assuming that this conjecture is true, he proved that the maximizer, this point Xn, converges in distribution to this unique maximizer of the Airy plus minus parabola when n goes to infinity. So it took almost 10 years to prove this conjecture. So the first result was by Corwin and Hammond in 2011. So they used some very nice properties of the Airy process, so-called Brown and Gibbs ensemble, Brown and Gibbs property. And a bit later, the same result, this conjecture was proved by Moreno Flores, Quastel, and Remenik, and they used completely different technique. So they computed the density of the maximizer of the Airy plus minus parabola. So they proved that this density integrates to 1, means that it defines probability distribution, and from this they managed to conclude that the maximizer should be almost surely unique. And a bit later, Leandro Pimentel also proved this conjecture using a completely different technique, and also he generalized this result for more general initial data when he considered the last passage speculation with paths going not just from the origin but from some curve. Then for sufficiently nice curves, he proved that again the maximizer of the limit will be unique. All right, this is the Johansson's conjecture.
Is the limit still like an Airy process minus parabola, even if the initial starting point is different?
No, it will be the KPZ fixed point.
Okay.
So if you look here, okay, so first of all, this Airy plus minus a parabola is the KPZ fixed point starting from the narrow wedge initial data at time 1.
Okay.
Okay, and then, so if we change the initial, this curve here, then here we'll get the KPZ fixed point at time 1. But this KPZ fixed point will be equal to this one only at the narrow wedge initial data.
Okay.
All right, so this is Johansson's conjecture, and so what I'm going to talk a bit later is we want to look in the case when this Johansson conjecture is violated. So we want to look at the cases when the Airy process has a non-unique maximizer. All right, for this we introduce a new parameter, a time parameter. Basically we take the last passage time g from the last passage speculation, and then we replace n by Tn. So T is now a new parameter which plays the role of time. Okay, so now we have two parameters, T and X. T is time, X is space. And on the right hand side we replace n by Tn, and then the randomness will come from a function Hn, which now depends on T and on X. Okay, it's a space-time function. And again, when we send n to infinity, in the limit we obtain a non-trivial limit, which is called the KPZ fixed point. All right, then, so roughly speaking, if we evaluate, so if we go back to the Airy process, then, so the Airy process is a particular case of the KPZ fixed point. And so the picture looks roughly speaking like this. We have some parabolic drift and some random fluctuations about parabola. Okay, then Johansson's conjecture says that at each time t, like this KPZ fixed point should have almost surely a unique maximum, unique maximizer. So we want to look at the points when the maximizer is not unique. Okay, so in other words, we define the random set, this capital T, curly T. This random set contains those times, little t, when the KPZ fixed point has more than one maximizer. Okay, this is the time of points at which the Johansson's conjecture is violated. And our result is the following. If we choose the initial condition for the KPZ fixed point nice enough, by nice enough, we mean that it should have parabolic decays at plus minus infinity, then the set of these time points where Johansson's conjecture is violated is non-empty with positive probability, and conditioned by this set, but by non-emptiness of this set, the Hausdorff dimension of this set T is almost surely 2/3. Okay, so are there any questions so far? Okay, so this is our main result. So before giving you an idea how to prove such a result, I want to overview briefly what is the KPZ fixed point and what we know about the KPZ fixed point. Okay, so the KPZ fixed point is a universal limit of just a large class of randomly growing interfaces under the 1 to 3 scaling. So if we take some randomly growing interface H from this class, so this H can be the function which we had before for the last passage calculation. It can be any other function. Then if we perform this 1 to 3 scaling by a small parameter epsilon, probably we need to subtract some time-dependent drift. Then when we send epsilon to 0, we expect to observe a non-trivial limit, and this non-trivial limit is called the KPZ fixed point. Okay, this limit is defined for quite a large class of initial data, and typically we consider the initial state of the KPZ fixed point any hypersemi-continuous function which doesn't go to infinity very fast. All right, so the KPZ fixed point has been first constructed by myself, Quastel, and Remenik in 2017. So it has been constructed as a limit of one particular model in the KPZ universality class, the totally symmetric simple exclusion process. So we managed to prove that the KPZ fixed point is a failure process in time on the space of upper semi-continuous functions. And moreover, we have a formula, explicit formula for the distribution function of the KPZ fixed point. So for any lower semi-continuous function G, the probability that the KPZ fixed point at time t stays below G is given by a Fredholm determinant. And the Fredholm determinant is computed with a kernel K, which depends on the time t, the initial state of the KPZ fixed point, and the function G. So there is an explicit formula for this kernel, but so it's quite complicated. It's not very important to provide it here. All right, so our characterization was kind of for any fixed initial data. But then this there was another more general characterization which appeared quite soon. Okay, so Duncan, whose last name I'm unable to pronounce, and Ortman and Virac constructed the so-called random directed landscape. And using this random directed landscape, they managed to give, so they gave another definition of the KPZ fixed point. So the KPZ fixed point, HT, started from the initial state H0, is given by the following variational formula, the supremum over the initial state minus parabola minus some random field A. And this random field is called the Airy sheet. And this random field minus this parabola, they called the random directed landscape. Okay, so so we had two definitions of the KPZ fixed point, our formulas and this variational formula. And recently, Mihai Nica, Quastel, Remenik managed to prove that these two definitions of the KPZ fixed point are the same. So basically, we constructed our definition from TASEP. They constructed the definition from the Brownian last passage calculation. And Nica, Quastel, and Remenik, they repeated our computations, but not for TASEP, but for Brownian last passage calculation. So they obtained the same formula. So basically, and what it means that for the same model, we have two formulas, meaning that these two should be equivalent. Okay, so now we have two characterizations of the KPZ fixed point, using the explicit formula and using the variational formula. And it appears that when we perform some analysis of the KPZ fixed point, like these two different formulas, they can be useful in different contexts. At some point, this formula is more useful. At another point, this one is more useful. And in fact, in our work, we have to mix like these two formulas. And so I'm going to talk about it a bit later. Yeah, so that's what we know about the KPZ fixed point. Then, so I recall what we want to prove is that the Hausdorff dimension of the times when the KPZ fixed point has several maximizers is 2/3. So then the strategy of proof is standard. We need to obtain the lower and upper bounds on the Hausdorff measure of this set. So first, we need to choose suitable covering of the set by some sets I, such that the expected Hausdorff measure of the set T is bounded by like the sum over these coverings, over the sets in the covering, and each term in the sum is the diameter of the set to the power alpha. Okay, so if we show that this sum vanishes for any alpha greater than 2/3, then from here we conclude that the Hausdorff dimension for these values of alpha should be equal, so the Hausdorff measure should be equal to 0 for these values of alpha, meaning that the Hausdorff dimension should be bounded by 2/3 from above. Okay, and then the lower bound on the Hausdorff dimension goes like in the same flavor. We choose a suitable covering by some other sets Ji, then we bound the Hausdorff measure of dimension 2/3 from below by the sum over this covering minus some little constant eta. And then if we show that all this expression is positive, we obtain that the Hausdorff measure is positive, and it means that the Hausdorff dimension should be greater than 2/3. Okay, so just using these two bounds, we conclude that the Hausdorff dimension is equal to 2/3. So now the whole challenge is how to prove these bounds, the upper bound and the lower bound. And it happened that for the upper bound, it is more useful to use our formula for the KPZ fixed point. But for the lower bound, our formula appears useless. Well, it's not that it's useless, it's just very hard to get any reasonable result from our formula. And in this, for the lower bound on the Hausdorff dimension, we need to use the variational formula for the KPZ fixed point. All right. Okay, so now I will try to give you a very sketchy idea how we prove how we solve our problem. So first of all, we define a set of functions. So we call it twin peaks functions. These are the functions which are very close to having two maximizers. So more precisely, this space TP twin peaks parameterized by two parameters and A and epsilon. So it contains those functions for which there are two values, x1 and x2, and at these points x1 and x2, the value of the function f is epsilon close to the maximum. Okay, so for example, in this picture at x1 it has a maximum, but at x2 it is not the maximum, but it is epsilon close to the maximum. Okay, so we consider this set of twin peaks function. And then the key result is what is the probability for the KPG fixed point to have twin peaks? And we can estimate this probability from above by epsilon t to the minus 1/3. Okay, so when epsilon goes to 0, then so this probability vanishes, which makes sense because typically we expect to have a unique maximizer for fixed time t. And then when t varies, this estimate tells us how the probability changes when t varies. All right, so first I will tell you how to get a bound on the probability like this, and then I will try to explain you how to use this this bound to prove the upper bound on the Hausdorff dimension which we want.
Can you please repeat the definition of twin peaks set?
Yeah, so it's just much easier to look at the picture. So we have a function which decays at infinity sufficiently fast. Usually we consider parabolic decay at infinity. And then there are 2 points x1 and x2 with the distance between them greater than a. This a is a constant here. And at these points x1 and x2, the value of f is epsilon close to the maximum. Okay, so here we have maximum, here we have maximum minus epsilon. Okay. All right. Are there any other questions so far?
So here you have this condition that maximum of f minus f of x are greater than epsilon. Should it be less than or equal to epsilon?
Oops, sorry. Yeah, this is less or equal than epsilon. Yeah, that is the typo. Yeah, of course. Otherwise, it doesn't make any sense. Yeah.
Thank you.
So we should be epsilon close to the maximum on these 2 points. So very simply.
I also have another question. So the 1/3 exponent in the key result. So the origin of this 1/3 is the same as the characteristic exponent of the KPG, or it has a different origin?
Yes. Yeah, basically it comes from the scaling identity for the KPG fixed point. And so a bit later I will tell you how it appears, I think on the next slide. Yeah, so okay, so now I will try to explain you how to get this bound, or at least how to get this exponent of t. Okay, so we do the following. We look at the KPG fixed point, and we look at 2 points which are epsilon at which the KPG fixed point is epsilon close to the maximum. Okay, then x1 and x2 will be random points, and the maximal value will be also a random point. So, and we compute the density of the maximal value and x1 and x2 simultaneously. Right, so for 2 parameters epsilon and delta, we define the following function. P, it depends on the time variable, depends on M. M is the maximal value. X1 and X2 are these 2 points, 2 maximizers from the previous picture. Okay, so the formal definition of this function is the following. So the KPZ fixed point always stays below M, but at these points, so in the delta neighborhood of the points X1 and X2, it gets epsilon close to the M, to the maximum M. All right, so from this definition, you can see that this is the probability that the maximum of the KPZ fixed point at time t is epsilon close to M, and in delta neighborhood of X1 and X2, the value of the KPZ fixed point gets close to M. Okay, so in some sense, this is approximation to the density of these points X1, X2, and M. And in fact, this is what we compute. So we compute the following limit. We divide this function by epsilon squared delta squared and then send epsilon delta to 0. And we prove that the limit exists. So why epsilon squared delta squared? Because we have 2 points, X1 and X2. For each point, we have 2 parameters, epsilon and delta. So two parameters, 2 points. That's why we need to define by this expression. Okay, so in principle, we don't know whether the limit which we obtain is, in fact, the density of some probability measure. It's not clear if we integrate over X1, X2, and M, if we get 1. But what is important that we have a limit, and we know some properties of this limit, and for us it is enough. Okay, so then how we prove that this limit exists? This is exactly the place where we need to use our formula for the KPZ fixed point. So if you look at the definition of this function P, it can be written as a linear combination of distribution functions of the KPZ fixed point. Okay, and so for the distribution function of the KPZ fixed point, we have a formula which is given by the determinant of some kernel. And then if we write everything carefully, taking this limit corresponds to some different, to taking derivatives of the determinant where this kernel depends on this parameter epsilon and delta. Okay, so these are quite difficult and lengthy computations, but in the end, if we perform this, we obtain that this limit is given by some linear combination of 4 determinants, and we have explicit formulas for the kernels of these determinants. Again, so like just looking at this formula, it is very difficult even to prove that the limit which you obtain is positive. But we will be interested in the upper bound on this quantity, and it appears that the upper bounds on Fredholm determinants are quite easy to obtain. Okay, in particular from this exact formula, we can compute the, we can get the following properties. First of all, this density P has a scaling property. So we can turn the time variable t to 1, but then we need to scale all the parameters. We need to scale the value of P, we need to scale M, X1, X2. And this scaling basically follows from the scaling of the KPZ fixed point. So the KPZ fixed point is invariant under the 1 to 3 scaling. And moreover, we can obtain the upper bound on this density. Okay. Okay, so this upper bound is a bit imprecise because when X1 tends to X2, this density explodes. But so basically what we do, we always separate X1 and X2 by some constant, and then we have a uniform bound on the density. All right, so as soon as we have this density function, we can show our key result, the probability that the KPZ fixed point has twin peaks. Okay, so roughly speaking, this probability is bounded by these 3 sums over X1, X2, and M of our approximation of the density function. Okay, so roughly speaking, we sum over all maximal values of the KPZ fixed point, and we sum over all points X1 and X2 where the KPZ fixed point is close to the maximum. So now we want to turn the sums into integrals, and we remember that we divided p by epsilon squared delta squared. So in order to turn the sums over x1 and x2 to integrals, we need to multiply them by delta squared, and the sum over m should be multiplied by epsilon to get an integral. And we have some extra epsilon, which came from the limit of this function p. So what we obtain is that some constant times epsilon and times the same expression where we replaced the discrete expressions by the limiting expressions. So now we can apply the scaling identity for the density function p. And if we simply change variables in these three integrals, we obtain the power 2 to the minus 1/3 in front. Okay, so here is our epsilon t to the minus 1/3. And what is left to show that this integral is finite. And okay, so this is another difficult task, but so we can do it. So this is roughly speaking the proof of our key result. All right, I hope it's clear. All right, now, so having this bound on the probability to get twin peaks, how can you get the upper bound on the Hausdorff dimension?
So one thing is that this mathcal p epsilon delta tm, in the definition of that, you have this height function ht. Is it this? What will be the correct way? Is it like the stationary version, which is like the one with the parabola added with it?
Here?
Yeah.
Well, this is the KPZ fixed point.
I see.
So we consider quite general initial data. But basically, we consider any initial data with parabolic decay at infinity.
I see.
So of course, it can be also the Airy process minus parabola.
Thank you.
Okay. All right, so now I will give you an argument how to prove the upper bound. And here I will go just line by line. Then I hope it will be much easier to follow. So first of all, we define a new set, set of times parameterized by new parameter a. And this is the set of times t when the KPZ fixed point has two maximizers at distance greater than a. Okay, so we separate maximizers by some constant a. So we estimate the Hausdorff dimension of this set. So we choose the following covering of this set. So we take the dyadic partition, the usual dyadic partition, with some fixed value little n. And we define sets capital I, which are just the sets around the of radius 2 to the minus n minus 1 around this point capital T. And then we cover our set T by the union of these sets I. Okay, so we don't need to consider all the sets I. We consider only those which have intersection with our set T. So basically this set Bn contains those indices for which I has intersection with the set T. Okay, then the claim is the following. We want to prove that at this point, bold T, the KPZ fixed point has twin peaks with a suitable value of epsilon. So epsilon will be some constant times 2 to the minus n over 3. All right, so how do we do it? So if the intersection of I and T is non-zero, is not empty, then just by definition it means that there is time point and x1 and x2 such that the maximum of ht is equal to maximum is equal to the values of h at x1 and at x2. This is just a definition. And we estimate the following expectation. we estimate the distance between the maximum of the KPZ fixed point at both t and the value of the KPZ fixed point at both t time and at the points xl, where this xl are x1 and x2. Okay, just we have a simple estimate by the sum of two expectations. So inside the first expectation, we use the non-Hölder regularity of the KPZ fixed point, which is 1/3. So the first term is bounded by bold t minus t to the power 1/3. So in the second expectation, we need the same estimate, but now for the maximal values of the KPZ fixed point. Okay, so we need to know the Hölder regularity of the maximum of the KPZ fixed point. And so it hasn't been known, we had to prove it. It's not completely easy, but basically it is not difficult to imagine that the maximal value has the same Hölder regularity 1/3. Okay, so in other words, the distance of h bold t minus maximum of the KPZ fixed point is bounded by some constant to the times 2 to the minus n/3. And this 2 to the minus n comes from the fact that t, the time t, belongs to the set I. So the distance between bold t and t is bounded by 2 to the minus n. Okay, so and this is roughly speaking the proof of our claim. So at this time point ti, the KPZ fixed point has twin peaks with this value of epsilon. All right. So now we bound the expected Hausdorff measure by the sum over the sets, the diameters of the sets to the power alpha. So the diameter of each set is constant times 2 to the minus alpha n. And we need to bound the expectation of the magnitude of the set of indices over which we sum. Okay, then from our claim, we can conclude that this expectation of the set of indices is bounded by the sum of probabilities that KPZ fixed point at bold ti has twin peaks. Then if we use our key result, then this sum is bounded by a constant times the sum over values of I, epsilon t to the minus 1/3. Okay, so now, so we recall the definition of epsilon. Epsilon is of order 2 to the minus n/3. Then the definition of bold t was 2 to the minus ni. So these powers of n, they cancel out. We have a sum over I to the minus 1/3. And then the values of I vary from an interval of size of order 2 to the n. So it means that this sum of i's will be bounded by 2 to the 2n/3. Okay, so if we plug in this estimate which we obtained into our bound on the Hausdorff measure, we obtain the following. The expected Hausdorff measure is bounded by 2 to this power of 2. And if alpha is greater than 2/3, then the right-hand side vanishes when n goes to infinity. Okay, so from here we conclude that for these values of alpha, the Hausdorff measure is almost surely 0. It means that the Hausdorff dimension should be almost surely smaller than 2/3. All right, are there any questions so far? Okay, so now how can we obtain the same upper bound? The standard approach to obtain to get a lower bound on the Hausdorff dimension is to define local times. So we define local time mu on some interval AB is roughly speaking the measure of times which the KPZ fixed point spans in the set of twin peaks. Okay, so analysis of these quantities very non-trivial, and this is still work in progress. There is still something has to be done. But basically what we can obtain is the following, that this local time has regularity 2/3, meaning that if you look at the interval of size delta, the local time of this interval is bounded by delta 2/3. So this local time is sub-additive. The local mu of some set is bounded by the sum over mu of subsets J, where J, the union of J is a covering of the set S. And we can also prove positivity. So on any interval, mu is positive, and we can even take lim infin epsilon, and we still have a positive value. And so roughly speaking, these two properties of the local time are enough to prove the lower bound on the Hausdorff dimension. Okay, again, so we choose a suitable partition, suitable covering of our set. So this time we can define sets Ji, which is just the sets of lengths 1 over n, I minus 1 over n, I over n. And then we define the set Sn, which is the union of those J which have intersection with our set T. Okay, then, so what we have is the following. These sets Sn monotonically converge when n goes to infinity to our set T. And from the monotonicity of the Hausdorff measure, we can conclude that the Hausdorff measure of T is a limit of the Hausdorff measures of Sn when n goes to infinity. Okay, so now the task is to bound the Hausdorff measures of these sets Sn, and we do it in the following way. So first of all, we use the definition of the Hausdorff measure. The Hausdorff measure of Sn is bounded by the sum over the sets, diameter of the sets to the power 2/3 minus some constant eta. So we want to choose eta, some very small positive constant. And now we can use regularity of the local time. So the diameter of the set to the power 2/3 can be bounded from below by the local time of this set. All right, now we use the subadditivity of the local time, meaning that the sum of this local times is bounded from below by the local time of the union. And so now we need to show that this expression is strictly positive. So basically, the argument is that the local time is strictly positive, and we can choose eta as small as we want, and also positive. So with a suitable choice of eta, we can make this expression strictly positive. And so from this we conclude that the Hausdorff measure of Sn is strictly positive. So taking the limit when n goes to infinity, we conclude that the Hausdorff measure of our set T is strictly positive. And from here we conclude that the Hausdorff dimension of the set is greater or equal than 2/3. So we obtain the upper bound, the lower bound for this set. It means the Hausdorff dimension of this set is equal to 2/3. And now, just using a simple monotonicity of the Hausdorff measure, we can take a to be zero, a to go to 0, and we conclude. So when a goes to 0, then this set T will be just the set of all times when the Kaplan fixed point has a non-unique maximizer. And then just by simple argument, we conclude that the Hausdorff dimension of this set when a goes to 0 is also 2/3. And I will stop here.
Okay. Thank you, Konstantin, for that nice talk. If anyone has questions, he can just unmute himself and ask.
I have a question. Why do we want to know the Hausdorff dimension? What does this tell us?
Oh, this is the most complicated question.
Sorry.
Well, roughly speaking, there is no particular reason why we want to know it. This is mostly out of curiosity. But it has a very like these sets have very nice physical meanings. So if you look at the last partial speculation model, so we can consider this upright path as polymers. Okay, and then when we take the limit, so Johansson's conjecture says that there is almost surely a unique maximizing polymer. It's called a polymer in zero temperature. All right. So if this polymer is non-unique, so basically we have two polymers with equal energy, and these are some very special critical times, like they're called exceptional times, when something something unusual happens in the system. So we have a kind of evolving polymer which evolves nicely, but at this exceptional time, this polymer jumps to another point. So it's a kind of jumping points of the end of the polymer, and we just want to study the set of these exceptional times. Yeah, so it just has a very nice physical meaning, but yeah, I don't think I can say anything more specific.
So you had defined this measure, the mu of AB, like is equals to 1 over epsilon, Lebesgue measure or something.
Yes.
So how is there like a intuitive way to like see why this regularity would be delta to the power 2/3?
Yeah, so again, this exponential is related to the scaling invariance of the KPZ fixed point. So let me see if I can.
If you like, and other question is like here for proving this, do you also use the exact formula?
Yes and no. So the exact formula is useful for upper bounds, like for the first property, regularity and subadditivity.
Mm-hmm.
But then it is it is very difficult to get positivity, strict positivity from the the exact formula. And here we use this variation of formula in the approach by Duncan, and Balint. Yeah, so it's the problem with these exact formulas is always the same. They're useful to get upper bounds, but they're very difficult to work with when you want lower bounds.
I see.
So in the next slide, like for Sn, you obtain an uniform lower bound for that measure mu local time.
Well, this is more complicated, so let me see.
Like you will be taking limit n tends to infinity. So
right. We have uniform local bound in n. Yeah.
okay.
So we have uniform local bound in n and epsilon. That's true.
See.
Yeah. This is because exactly what you said. We need to send n to infinity when we still want to have something positive in the limit.
Is it intuitively obvious because Sn is kind of random?
Well, this is highly non-obvious.
I see.
Yeah.
Okay.
So
Well,
I have a question about, sorry, somebody else was talking? Okay, so I have a question about this parabolic decay assumption. So I'm not completely familiar with this assumption. So, for example, I know that with the droplet initial condition, you have the parabolic decay,
Right.
because it's a Airy process minus a parabola. But for example, for a stationary initial condition or a flat initial condition, do you also have this sort of decay?
No. Yeah. So, okay. So first of all, why do we want this parabolic decay? So we want uniqueness of the maximizer. So we want almost surely uniqueness of maximizer. And then if we take, for example, flat initial data, then the maximizer is almost surely non-unique. Or maybe it is even surely non-unique. Well, basically we don't have uniqueness of the maximizer. Yeah, probably I'm not completely sure. Maybe we can. Maybe we don't need to require parabolic decay. Maybe we can require some weaker decay. But in any case, we need decay to infinity. Yeah. So when you start the KPZ fixed point with flat initial data, it will be roughly speaking a curve, and then like a line, straight line, and then random fluctuations around this straight line. And then like our question doesn't make much sense in this context. And the same about the stationary case.
Last question is like, is there a possibility this exact for computations with the formula can be done by like this JIPS property or?
Well, this I don't know, because I'm not an expert in this. I'm not an expert in this, and I can't really tell you.
Okay.
But well, like we discussed this stuff with Ivan and with Alan, they definitely know much more about this Brown-Gibbs property, and so they're quite happy with using this exact formulas for the upper bound.
I see.
So it means that like it makes sense to use these exact formulas.
Thank you.
You're welcome.
okay, so if there is no other questions, let's thank the speaker again. So I guess that's it. So we will meet again next week. Thank you, everyone.
Konstantin, I still had one question actually, of a technical variety.
Okay, so what is the question?
Yeah, so in your upper bound, you mentioned that you have to obtain the same type of regularity for the maximum as opposed to just taking a generic deterministic time.
Right.
And I realize that it's a technical question, but I suspect that it's rather important in how you do this. Do you mind saying a word about how to transfer this regularity over to the maximum?
Yeah, so here we use a variational formula for the KPZ fixed point. Okay. So where is it? yeah, so we need to use this variational formula, and yeah, so we have very good bounds on the Airy sheet, and then yeah, just this Hölder regulator of the maximum just boils down to some manipulations with the Airy sheet.
Okay, so taking estimates from the DOV paper.
Right.
Okay. Thank you.
You're welcome.